Hello students, welcome to the class. So today we will start with the section 6.2 of the NCERT chapter 6 equilibrium. We have already dealt with the physical process. Now in today's class our objective would be to look at the physical chemical process. And why I have defined the physical process first? Because it is easier to understand equilibrium in terms of physical process, because there you have physical things changing, like your color, your, I would say, the state and all of that, and that is visible through the naked eyes. But if you are considering the chemical process, then things become a bit complicated. So we'll try to understand that same, and after understanding this chemical process equilibria, we will give some characteristics of the same. If I talk about the specific section that I am covering according to the NCERT, then first thing we are seeing is obviously your equilibrium in chemical process, which is dynamic equilibrium, section 6.2. Then we have a practice problem, and after that there is a exercise question, NCERT exercise question 6.1. So let us discuss our part of chemical equilibrium. So whenever you see a reversible chemical reaction where your rate of forward and backward reaction are equal, then in that case you say that your reaction is in equilibrium state. Now the definition is simple. Then why it is difficult to understand? Because in compared to the physical process, here you have to look upon the concentration term. You cannot judge the concentration of a given chemical reaction with your naked eyes. It is impossible. Suppose I give you a sugar solution and say that, okay, tell me that what is the amount of sugar which is dissolved. So you cannot say it without measuring it. So to measure the concentration thing is very, very difficult. But if I tell you that, can you see the intensified violet color of the iodine? You will say, yes, obviously it is observed by looking at the system itself. Right? So for that reason, your physical process are easier to interpret and easier to understand. But due to this concentration part, the chemical reactions are somewhat difficult. Now there is a term in this, reversible reaction. We are saying that the equilibrium is attained in a reversible reaction only, and at that point where your forward and backward reaction are occurring at the same rate. Now what is the reversible reaction? So this term is obviously self-explanatory. How? Because reversible means what? Means it can proceed both in backward and forward direction. Means at any point of reaction, you can just go back to the reactant side from the product side. And this condition is being represented by a double hooked arrow. Let us take an example. Suppose we have a condition where a reactant is in equilibrium with the product. Now we have a graph related to the same. What is this graph depicting? So two things are noteworthy here. First is that a red line is being there, which is saying that your reactant concentration is decreasing with time. So first it is at a higher altitude, then it is decreasing, and after a certain time it is becoming constant. Suppose we say that this point, this dashed point is representing the point where your concentration is now constant. Now if you look at the product concentration at the same instant, you will also notice that the product concentration has also now become constant. It is initially rising, and it is obvious because whenever you do a reaction, the reactants will get converted into product. So product concentration will increase and reactants concentration will decrease. But after a certain point, both of these will have the constant concentration, right? And this point where this concentration of the reactants and products become constant, we say that point as the equilibrium state. Got it? So this dotted line is representing the start of the equilibrium state. Now, at equilibrium, what will happen? Obviously, we have told you that the rate of forward reaction and the rate of backward reaction will be equal. Now, if this is equal, that means the concentration of the reactant and the concentration of the product will not change with time. They will be at a steady level. Now, let us try to understand the same with the help of a rate part. So we have already seen the concentration part. What will happen to the rate graph? So if you look at the rate graph, then you will see that both of the lines are merging. This thing is possible for concentration also, but not mandatory for concentration graph. But the merging of two lines is mandatory for the rate of reaction graph, because both rates should be equal, not only constant, both rates should be equal. Suppose this is the rate of forward reaction, it will slowly decrease, because as soon as the product start to form, so at the start the product formation will be faster because more reactants are present. After some time it will get slower, and at a time it will become constant. Similarly, your reverse reaction will hype out. Okay, so it will start to increase. Initially more reactants are there, products are present in a lower concentration, so the forward reaction is favored and the reverse reaction is occurring at a slow rate. But as soon as the product concentration increases, the chance of reverse reaction also becomes faster. So it slowly starts to increase, and after a time it also becomes constant. Now at this green part, where the rate of forward reaction and the rate of backward reaction become constant and equal, this part is called as equilibrium. So initially what we have, the red line, which is at a higher state where only the reactants are present, so it will start to decrease after some time. At the same time, the blue part will start to decrease. When there is no product, there is no reverse reaction, it is completely zero. But at equilibrium, what will happen? Both of them will merge. So this is a must point for this graph. Now again I am repeating it, for the concentration part this merging is possible but not mandatory, but for the rate of reaction part this merging is important. And at last we can say that this green line, where the red line and blue line has merged, this depicts your equilibrium state. Let us try to do a question on the same. So here are four graphs, and you have to say that which of the graph is correct, right? Which of the graph is correctly depicted. So there are various conditions from A going to B. So this is your equation. Your time to solve this question starts now. It's a very simple one. Remember, this is a closed container. You already know that if you are studying equilibrium, you will study this under a closed condition. Your time starts now. Just analyze each of this graph. See, two things are there. First is that the reactant's concentration will decrease and the product's concentration will increase with time. After a time, they both will become constant. Now, which of this graph is not following the same? Can you find it? It's an easy one. 10 more seconds for you. You have to find the incorrect one. Remember, you have to find the incorrect one. So, your time is up. Now, the incorrect graph will be the fourth one. Let's see how. As I have told you that if you want to study equilibrium, that one thing is for sure, that the reactant concentration will decrease with time because it is getting converted into product. Okay. But both cannot increase or decrease simultaneously. So this is not possible that the reactant's concentration and the product's concentration will increase or both will decrease. So this case is not possible at all. So of course, after some time, they both can become constant. So this can be possible, and this is only possible when the equilibrium is attained. Keeping these 3 points in your mind, we can say that the A, B and C graphs are correct, because initially they have some concentration. After some time, the concentration of the reactants is decreasing and the concentration of the products are increasing. And after this dotted situation, we have a equilibrium condition. I've told you already that both graphs can merge in case of concentration term. So this is not mandatory, but a case can arise at the same level. Now, what about D graph? If you look at the D graph, you will observe one thing. And that thing is, the concentration of the reactants and products both are decreasing. Now, it is not possible. If your product's concentration is decreasing, then it must be going to the reactant, but the reactant concentration is also decreasing at the same time, and it is not possible at all. Got it? So this thing is completely out of order. So we can say that since your both concentration of reactants and products are decreasing with time, So a reversible reaction is not possible here. Therefore, this is a impossible graph. Next is, what are the necessary conditions for chemical equilibrium? We have already seen some conditions. So the process should be reversible. It should be a closed system. Let us just list them. First is reversible reaction. So the reaction should can proceed in both forward and reverse direction. So this is mandatory. Second is the system should be closed, means the exchange of matter should not be allowed. The exchange of energy is allowed, obviously. Third thing, the concentration should be constant. Then and then only we will say that the equilibrium is attained. Okay. Fourth thing, the rate of forward and backward reaction should be same. So it's obvious. The rate at which the reactant is getting converted into product and the product is getting converted into reactant should be same. And the fifth thing, you have to keep the temperature and pressure constant. Why is it so? Because temperature can change the equilibrium. Constant, we'll study about this. It's very important. And same case can be said about pressure. So pressure does not alter the equilibrium constant, but it changes the state of equilibrium. Okay, so whenever you change the temperature and pressure, equilibrium will be disturbed and the equilibrium will try to shift in a different direction depending upon how the change is applied. We will talk about these factors, how the temperature and pressure changes the state of equilibrium. But for now, you should remember that these 5 things are must for equilibrium condition to sustain. The reaction should be reversible, the system should be closed, the concentration should be constant for both reactants and product, the rate of forward and backward should be equal, and the pressure and temperature should remain constant. Now let us take examples of chemical equilibrium to understand the concept in a deeper version. Suppose we are considering the Haber process. So here we are making ammonia from the nitrogen and dihydrogen. Okay. If you look at the graph, this graph would not look like a classical one that we have already seen. Why? Because there is no intervention of both the graphs. The red line is apart, the green line is apart, and the blue line is apart. There is no interception of both the line, and it will never happen in the future as well. Now what can be said about this graph? You can easily say that the concentration of the reactants, which is nitrogen and hydrogen, they are decreasing with time. So this is the first thing. Second thing, the concentration of products is increasing. You can see that the blue line, which is representing ammonia, it is increasing with time. And at a certain place, you will see that the slope of the graph becomes 0 for each of them. Means now the change in their concentration of reactant and product is no more being observable. So what we can say, that in this condition, the forward and reverse reaction are at equilibrium, or they are occurring at the same rate. Now why I am putting this example here? To make you understand that there is not a necessity for the graphs to intercept each other. They can be far apart also, still they will represent the case of equilibrium. Got it? Until and unless the reactants and products are being represented properly. So the previous case you have seen just now, where the reactants and products were both decreasing. So that cannot be possible at all. Okay, we can take more examples. Suppose we are taking the case for formation of HI from the H2 and I2, which is giving us hydrogen iodide. If you look at this graph, this is also a new one. Why? Because after some time, you will observe that this graph has gone to the up part. Okay, so it has become constant at a point, but after that point also, after remaining equilibrium for some time, the equilibrium is disturbed. Now what are the observations we can say? That the forward reaction is what? It is related to the decline of the H2 and I2, whereas the case of the reactant we can see that the HI concentration is increasing. Now this thing is happening until the equilibrium is attained. What about the backward reaction? So the backward reaction or the reverse reaction is the what? In which the HI is breaking down into H2 and I2. You can see at this, if you start from the right side of the graph, from this part, then on moving from right to left, the concentration of HI is what? It is decreasing, whereas the concentration of H2I2 is increasing. After some time, it becomes equal. So at this point, both the forward and backward reaction, the rates are equal. So there may be a chance that it is not constant till infinite time. They can be moving away or they can be intercepting as well. Now, the dotted line is showing that condition where the rates of forward and backward reactions are equal. Now, again, this graph is there to depict that there are multiple cases possible. Okay, you have to analyze them properly such that you can select the graph which is correct. So, this is also a very good question that can be framed. Now, we will introduce the concept of dynamic equilibrium in the case of chemical process. We know it very well. What are dynamic equilibrium? Where there is no net change of the reactants and product concentration, but the reaction is going in within the solution. Let us take a case to understand the same. So a thing which is called isotope tracing, I have introduced it here to make you understand the point. So what we are doing here, after attainment of the equilibrium, suppose the equilibrium is attained, then what we are doing, we are adding D2 to that equilibrium system. Now, as soon as you add D2, what will happen? You will see that your D2 and I2 are reacting. But D2 is what? It is simple deuterium, right? So it should not react. If the equilibrium process says that the process is not going any further, that means it shouldn't take part in the reaction because hydrogen has already attended the equilibrium along with the iodine. But it is seen that although the reaction is attended, if you add deuterium, then deuterium takes part in the reaction. Got it? And how it is confirmed? It is confirmed by the formation of Di. Similarly, you can see one more type of new species which is formed, which is HD, which is basically the product of D2 and HI reaction. So from here, you can say that due to the formation of Di and HD, we can clearly confirm that after reaching the equilibrium also, there can be reaction that must be going on inside the reaction mixture. Okay, so let us summarize all of this. So there will be dynamic equilibrium. First of all, we studied about dynamic equilibrium. Dynamic equilibrium is one where the rate of forward reaction and the backward rates are same, but the system is still doing the process. After that, in the dynamic equilibrium case, there must be a constant concentration of both the reactants and products. And it will be only seen in the chemical process when the reaction is reversible. And what is the reversible reaction? Which can proceed in both the ways. Next criteria for that should be the system should be closed, which is very important reason for the attainment of equilibrium. Then we have the next thing, which is the macroscopic properties like your color or the weight or the volume, concentration, that should not change with time in the case of equilibrium. What is dynamic nature? How is dynamic nature depicted? So we have seen the formation of Di and HD in the equilibrium mixture of H2, I2 and HI. So that clearly depicts that the nature of the equilibrium in case of chemical process is dynamic. So this was all for today's lecture. Thank you for attending the session. I hope you enjoyed it.